Let's look at some more reactions with alkynes, and specifically let's look at a hydration reaction, which is also an addition reaction. So we're just adding water across a triple bond. And it's very similar in a lot of ways to adding water across a double bond. So here I have an alkyne. I add water in the presence of an acid catalyst. I form this substituted. I have an OH here and I've added an H here. Notice in this case I have a special molecule. I have a carbon with an OH attached to it, and that same carbon has a double bond attached to it. It turns out that this molecule we call an enol because it's got an ene and an ol. So it's got alkene and an alcohol on the same carbon. It is actually in equilibrium with the ketone. And so it quickly changes, once I form this enol compound, it quickly changes over to this ketone compound. So how does that happen? Okay. So here's what's going on here. I actually have a alkene and an enol. So I have an ene and an ol on the same carbon here. We call that an enol. It actually changes over to ketone, and we call that a tautomerism. Okay, so whenever I form a enol, I know it tautomerizes immediately over to the carbonyl carbon here. In this case, the ketone. Let's look at the acid catalyzed mechanism for that. So here's my enol. My double bond here is still going to be nucleophilic. I'm going to draw these electrons down here to form a double bond to my carbon, pushing those electrons out to pick up that hydrogen, breaking that acid catalyst here to form this intermediate compound here. Notice here, all I have to do is deprotonate now this charged oxygen with hydrogen on it. So I have water sitting around. It's now acting as a base. Those lone pairs will form a bond to that hydrogen, breaking that bond, putting that lone pair back on oxygen to form the ketone. We're going to find out that this mechanism is very important in chemistry, and we'll learn about that next semester. So whenever I see a ketone, I could actually draw the enol form of it too, and then explain a lot of chemistry. Why is that carbon reacting and that carbon reacting? It's because of enol-keto interconversion, tautomerism. Okay. Let's look at a few examples. Here I have an internal alkyne. It happens to be symmetrical. So I have the same number of carbons on the left as I do on the right of my triple bond. I look at my reactants. I'm adding water with an acid catalyst. I know that forms the enol followed by tautomerism to form the ketone here. Okay. Because it's symmetrical, either one of these carbons that forms the ketone would give us the same final product. If I have an internal alkyne that's unsymmetrical or asymmetrical, I could either form the enol with the OH here or the OH here. So I get two different products that can tautomerize with my water and my sulfuric acid. So I get two products are formed in this case. So I form one where the carbonyl group is at carbon number 2, and the second one where the carbonyl group is at carbon number 3. There are other ways to do hydration reactions with terminal alkynes. They tend to be less reactive to addition reactions, so we need some sort of catalyst, and scientists have found that this mercuric ion is actually a good catalyst for forming the enol by adding water across a triple bond. So here is my terminal alkyne. Here's water, here's my acid, and here is my mercury ion catalyst now. It forms the internal enol, so there's no OH out here, and therefore I form the ketone. And this follows Markovnikov's rule again. I add the hydrogen to the least substituted, my OH to the most substituted, and then it tautomerizes. Let's look at the reaction mechanism for that. So my triple bond, those are going to be nucleophilic. The mercury ion in solution, because it's going to dissociate into the mercury +2 cation, it is actually going to be electrophilic. So I start to form and break bonds, forming this mercurinium complex here, which leaves one of these two carbons with a slight partial positive onto it, this one being the more stable, so my water attacks the internal carbon here. I then form the enol. I pick off that hydrogen here, pushing that down. I still have mercury on there. And in acid, it turns out that I can actually then break that bond, forming the enol compound, moving that oxygen out to that compound then. So this tautomerizes, and then I push that out, forming the enol itself. Okay, and then it tautomerizes again to form the ketone. How about hydroboration? Can I do that type of hydration reaction? Yes, I can. So I can take a triple bond, react it with a disubstituted boron compound in THF, tetrahydrofuran, that's just my solvent. I form this intermediate product here where I've added hydrogen, and then I have my boron complex here with two other substituents, react that with my hydrogen peroxide in a basic solution to form the enol. Once I've added that hydroxide and formed the enol, it's going to tautomerize again to form the ketone here. Okay, so typically we use this 9BBN, which is this disubstituted boron compound here, when we have terminal alkynes, but we could also use it for internal. But we typically use BH3, simple BH3, when we have internal alkynes also. Either tends to work fine. Okay, so let's look at some examples. So here I have a terminal alkyne. I react it with a boron compound that's disubstituted like 9BBN, and then I oxidize that with the hydroxide anion in hydrogen peroxide to form my enol, which tautomerizes to the aldehyde. Again, here I'm doing anti-Markovnikov addition, right? If I want to do Markovnikov addition, I'm going to use water and my mercury sulfate. So I'm going to form the internal hydroxyl enol here, which then tautomerizes to form the ketone. Let's now talk about hydrogenation reactions. Hydrogenation meaning I'm adding H2 across a triple. When I add hydrogen across a triple bond, I add one equivalent of hydrogen across that triple bond in the syn orientation, and then I form an alkene. This alkene is still attracted to my catalyst, so I can add a second equivalent of hydrogen across that double bond now. So in fact, I've gone from a alkyne with two elements of unsaturation all the way over to the alkane, which has 0 elements of unsaturation. If I look at the energy for breaking those bonds, you can see that it takes 226 kilojoules to actually break that first bond. And to break the second bond takes just a little bit more energy, and it continues on to form my alkane. It's energetically favorable to go all the way from the alkyne to the alkane. Sometimes we'd like to stop at the alkene, so we need some way of actually doing chemistry, and there's been some very sophisticated work done with catalysts where they take this palladium carbon and they poison it, make it not as good catalyst, so I can stop the reaction before I add to the pi bond. And one way to do that is using something called Lindlar's catalyst. So Lindlar developed this catalyst where he takes H2, he takes the catalyst palladium, which is suspended on a barium sulfate complex, and he adds in this base called quinoline in a methanol solvent. And what he found is that he can stop the reaction just about stoichiometrically at the cis alkene. It does not proceed onto the alkane. So the reaction is stopped after the addition of only 1 mole equivalent of hydrogen. This Lindlar's catalyst is composed of a powdered barium sulfate coated with palladium and poisoned with quinoline. And this reaction does proceed by the standard chemistry of adding in the syn direction to form cis stereochemistry of the alkene. It's a poisoned catalyst. So if I take a triple bond, in this case it's an internal triple bond, and I react it with Lindlar's catalyst in the presence of some hydrogen gas, I form the cis alkene. So I go from the 2-pentyne to the cis 2-pentene. So what is this catalyst doing? Okay, what a catalyst does is if I look at the reaction coordinate here, and I look at the reaction energy of a normal addition reaction of H2, I can actually, with the catalyst, I can reduce that activation energy. And with Lindlar's catalyst, I just don't reduce it as much, so I poison it. So both the substrates, hydrogen and alkyne, have to be absorbed first onto the catalyst surface, and that weakens one of the pi bonds, and then my hydrogen is added from the same side. I do not have enough energy based on that catalyst to actually add that second equivalent to the alkene. What if I want to get the trans addition of hydrogen? Actually, some scientists have found out that I can use a completely different process where I use this dissolved metal reduction process. In addition to calling this a reaction of adding hydrogen across a triple bond or a double bond as an addition reaction, we can also call it a reduction reaction. Because whenever I add hydrogen to a double bond, I'm actually reducing it. So I can look at the oxidative states of those two carbons. If I do this dissolved metal reduction, I actually form trans alkenes. So here are the reaction conditions. I have a alkyne. I put in there this sodium metal with some liquid ammonia at very cold temperatures. I can also use lithium as my dissolved metal. And I form this anti-addition of hydrogen across that triple bond, and it will stop at the double bond. So we use dry ice to keep the liquid ammonia liquid, and we add sodium metal dissolved in ammonia so it loses an electron. So what's happening here is I have the ammonia and I have the sodium at cold temperatures. I actually lose an electron. Okay, so I have these free electrons that are floating around in solution, and it turns out this complex here looks very brilliant blue. It's a deep blue color. So it's a real pretty reaction to actually do this dissolved metal reduction process. But why does it form the trans? Let's take a look at that. So here I have 2-octyne. I have sodium and ammonia. I recognize that that is a dissolved metal reaction. I haven't listed some of the other things here, like the temperature, etc. And I know I get 80% formation of the trans 2-octene. The other 20% is either the cis version or some other reduction product. Okay, so here I have my sodium with its electron on it. It can actually attack one of my carbons here, and I can then do radical chemistry where one of my electrons from one of my pi bonds goes over to this carbon to form this lone pair of electrons, leaving a single electron over here. That single electron can react with another radical sodium molecule to actually pick up one more electron. Okay, and then I can start adding hydrogens to both of these. In this case, my lone pair can add to my ammonia, picking off a hydrogen, and in this case I can also react with a hydrogen to pick off ammonia, and it leaves me with trans. Let's look a little closer at this reaction mechanism now, and let's look at some of the molecular orbitals that are formed when I actually react with this sodium radical. So here I am. I take an electron, I put it on that carbon, which moves one of the electrons back over to another carbon here, so both of them, so I have this radical here. It turns out that having these on opposite sides from each other is the most stable conformation, and having these on opposite sides is the most stable. These two groups are furthest apart, and these electrons, which are both negative, are furthest apart. Then my lone pair reacts with my hydrogen to pick it off of my ammonia, leaving another anion here. I now have this radical, this vinyl radical, which is very reactive. It picks up an electron from solution. Again, that's because my sodium in solution is just a source of electrons. So I make that a lone pair now anion. It goes and picks up a hydrogen from ammonia, breaking off ammonia again, and I get the trans. And the trans is, again, favored because my R groups are on opposite sides and my electrons are on opposite sides of my intermediate compounds. Let's do a practice exercise where we actually select the right chemistry for actually preparing these compounds here. So in all cases, I'm starting off with this cyclooctane. In this case, I'm going to get the octene. Let's see, if I just used palladium and carbon and hydrogen, I know that that's too aggressive, so I have to use something that is poison catalyst. So I'm going to use Lindlar's catalyst and hydrogen in this case. And that gives me syn addition and gives me the cis stereoisomer. If I look at this product, I actually end up with the trans isomer, and I know that's my dissolved metal chemistry. And finally, this last example over here, where I've gone from the alkyne to the alkane, I know I can use what I call a full strength catalyst, just hydrogen and palladium catalyst. Now let's look at some oxidation reactions. So if I were to look at an alkyne and react it with potassium permanganate with water in a neutral solution, meaning not acid or basis, I tend to form this tetrahydroxide compound, which then spontaneously loses water to form the diketone. Okay. If I heat this up just a little bit, this reaction actually cleaves the triple bond. So in this case, if I have 2-pentyne in the presence of potassium permanganate in basic conditions with some heat, I actually will cleave that triple bond and then oxidize those two carbons up to the carboxylic acid. I first, in basic solution, I form the carboxylates, throw in some acid to form the carboxylic acid. So it's a two-step process. First forming the carboxylates, then forming the carboxylic acids. Okay. Let's look at a few more examples. If I take 1-hexyne in the presence of potassium permanganate, basic solution in water, and probably a little bit of heat here, I cleave that triple bond and I form the carboxylates. I then need to throw in some acid to form the carboxylic acids. It turns out that this formate with just one hydrogen on it, it tends to be oxidized up to the CO2. So my end products are a carbonic acid, and which then oxidizes up to CO2. Okay. So in the overall reaction, I have two steps here. First is my oxidizing reaction, then followed by my acidification. I've formed pentanoic acid, 1, 2, 3, 4, 5 carbons, and I form CO2. You can see here, if I were to split down here, I get 1 carbon and I get 5 carbons. Okay. Let's look at some products that you would expect, depending on whether I expose them to a dilute neutral KMNOH or warm basic KMNH. So if I look at 1-hexyne, if I look at neutral potassium permanganate, I know I'm going to oxidize those up to the ketone, but because I'm terminal, that's going to continue to oxidize up to the carboxylic acid, but I'm not going to cleave that triple bond. If I warm it up and add some base, I know I'm going to cleave it, so I'm going to form the carboxylic acid and CO2. If I look at 2-hexyne, if I just react it with dilute neutral, I'm going to form the diketone. Warm it up and add some base, I'm going to cleave that to form 2 carboxylic acids. 1, 2, 3, 4 carbons and 2 carbon. So 1, 2, 3, 4, and 2 carbons. I just split it right down through the triple bond. 3-hexyne, do the same thing. Form the diketone. And then I'm going to actually form 2 equivalents of this propanoic acid here because it's a symmetrical molecule. If I look at 2-methyl-3-hexyne, if I expose it to dilute neutral potassium permanganate, I form the diketone. If I warm it up and add base, I'm going to cleave that. In this case, I'm going to get 2 different products. One's going to be the propanoic acid, and the other one is going to be 2-methylpropanoic acid. We're going to learn those nomenclatures in the second semester of organic chemistry. Now let's look at cyclodecane. This is an interesting one. It's a cyclic compound. If I expose it to dilute neutral potassium permanganate, I form the diketone. If I warm it up and add base, I know I'm going to actually cleave that molecule, okay, and open it up. So this is an interesting way to actually form diacids, is first form a cyclic compound, form the triple bond, and then cleave it using potassium permanganate. We also talked about using ozone to actually cleave double bonds, and that also works for alkynes. So here, if I have this diene here, I'm actually going to cleave both of these double bonds, and then I add in a second step, I reduce it using this disulfide. I could also do ozonolysis of alkynes. I'm going to cleave that double bond and then oxidize those 2 carbons, 1 carbon and the 2 carbon, up to the carboxylic acids. Notice also that this is a 2-step process because I still need to add the hydrogens to these oxygens here. Let's look at a few examples. Here I have an internal alkyne, and there's 7 carbons, so it's 1, 2, it's a 3 alkyne. Ozone, I know I'm going to cleave it, and then I'm going to add water to protonate those carboxylates to form 2 different carboxylic acids. The same thing here. I'm going to cleave that triple bond, forming 2 carboxylic acids. And finally, here I'm going to cleave that double bond. However, when I cleave that, I'm left with this 1 carbon attached to some other alkyl group. I can understand that, but I'm also have a single carbon here, so I'm going to oxidize that single carbon up to CO2 also.